Greetings, esteemed readers. I am Frelyn Charmaine, and it is my privilege to guide you through an insightful exploration of the intricate realm of developing safety-critical systems. In a world increasingly reliant on sophisticated technologies, the significance of safety-critical systems cannot be overstated. These systems, embedded in vital sectors such as healthcare, transportation, and energy, play a pivotal role in safeguarding lives and mitigating potential disasters. The development of safety-critical systems introduces a heightened level of responsibility due to the potential deadly consequences of software defects. Balancing quality with factors like cost, ease of use, and time to market requires careful ethical consideration. Safety-critical systems, integral to products from automobiles to medical devices, rely on flawless software performance. The process demands expertise from highly trained professionals, rigorous methods, and advanced tools. Neglecting to address software errors in these systems is deemed unprofessional and can result in disastrous outcomes, emphasizing the critical need for stringent measures and constant vigilance in their development. Here's a detailed explanation and scenario. Safety-critical system failures. Example 1. Toyota's uncontrollable acceleration and faulty braking system. In this scenario, a safety-critical system failure occurred in Toyota vehicles due to issues with uncontrollable acceleration and a faulty anti-lock braking system. These defects resulted in tragic incidents causing loss of lives, compelling Toyota to initiate 3 separate recalls. The financial toll on the company amounted to nearly $3 billion. The software malfunction led to an ethical dilemma for Toyota, requiring a delicate balance between rectifying the issue promptly and addressing the financial repercussions of the recalls. Example 2. Covidien's neonatal ventilator recall. Covidien faced a safety-critical system failure involving neonatal ventilators. A software problem compromised the delivery of air to patients, falling below the levels specified by physicians or nurses. This critical issue had the potential to cause serious injury or even death to newborns relying on these ventilators. Consequently, Covidien had to issue a recall, highlighting the ethical responsibility to prioritize patient safety over financial considerations. Example 3. General Motors defective airbags. In another instance, General Motors encountered a safety-critical system failure affecting as many as 4.3 million cars and trucks. The problem lay in potentially defective airbags that might fail to deploy in an accident due to flawed embedded software. This posed a significant risk to the safety of vehicle occupants. To mitigate the potential harm, General Motors had to recall the affected vehicles, emphasizing the complex decisions companies face in balancing safety, financial implications, and reputation. Scenario recap. Imagine a family purchasing a Toyota vehicle, trusting in its safety features. However, a flaw in the anti-lock braking system and uncontrollable acceleration leads to a tragic accident. In another scenario, a newborn in a hospital relies on a ventilator manufactured by Covidien. Due to a software glitch, the ventilator fails to deliver the necessary air, jeopardizing the infant's life. Furthermore, consider individuals driving General Motors vehicles with defective airbags. In an unfortunate accident, the airbags fail to deploy due to flawed embedded software, increasing the risk of severe injuries. These examples underscore the critical importance of ensuring the flawless performance of software in safety-critical systems to prevent life-threatening consequences. Developing safety-critical systems requires an essential shift in perspective. Contrary to the assumption that safety automatically follows a standard development methodology, safety-critical software demands a more exhaustive and time-intensive process. All tasks, from requirement definition to implementation, necessitate additional steps, thorough documentation, and meticulous checking. This heightened scrutiny extends the development timeline, making safety-critical software both time-consuming and expensive. Next, we will tackle about system safety engineers' crucial role in safety-critical systems. In the realm of safety-critical systems, the appointment of a system safety engineer stands as a cornerstone. This professional carries explicit responsibility for the system's safety, overseeing a comprehensive approach. The safety engineer utilizes a logging and monitoring system, meticulously tracking hazards from project initiation to completion. A hazard log, integral at each software development stage, evaluates how detected hazards are addressed. Regular safety reviews occur throughout the development process, supported by a robust configuration management system that tracks all safety-related aspects. Crucially, the safety engineer's role extends beyond documentation. While producing a hazard log is part of the responsibility, their primary objective is to wield influence over the system's design. This proactive engagement ensures that the system, once operational, adheres to the highest safety standards. In essence, the system's safety engineer is not just a recorder, but a pivotal influencer in crafting a safety-centric system from its conceptualization to real-world application. Navigating ethical dilemmas in safety-critical software development. The prolonged timeline and heightened costs associated with safety-critical software development introduce ethical considerations for developers. An ethical dilemma emerges when deciding on hardware mechanisms to reinforce critical software functions. While these measures enhance safety and mitigate software defects consequences, they might escalate manufacturing expenses or complicate user operation, potentially diminishing product appeal compared to competitors. Companies face the delicate task of striking a balance between creating the safest possible product and meeting customer preferences. This involves careful consideration of cost implications, user-friendliness, and market competitiveness. Furthermore, determining the sufficiency of testing poses another ethical quandary. In the context of products with potential life-threatening implications, such as safety-critical systems, software developers must grapple with the question of when quality assurance (QA) activities are adequate. A pivotal decision point arises where developers must confidently sign off on QA, acknowledging that the product has undergone rigorous testing. This decision demands a nuanced and careful approach, reflecting the ethical responsibility inherent in developing products where failure could result in loss of human life. Striking the right balance between thorough testing and timely product delivery requires a judicious and considerate decision-making process. Addressing deficiencies in the F-35 stealth fighter. In October 2015, Dr. J. Michael Gilmore, the Director of Operational Test and Evaluation for the U.S. Department of Defense, brought attention to critical concerns in the advanced F-35 stealth fighter. His memo identified a total of 27 Category 1 and 64 Category 2 deficiencies, with a significant number attributed to software-related issues. Category 1 deficiencies, as defined, pose severe risks, including potential for death, severe injury, or occupational illness. They could also lead to major damage to the weapon system, critically impede combat readiness, or result in a production line stoppage. On the other hand, Category 2 deficiencies, while not directly life-threatening, still impede or constrain successful mission accomplishment. The U.S. military faces a complex decision-making process, balancing the imperative to eliminate these deficiencies for the safety of personnel and equipment with the need to bring the aircraft into service promptly while managing project costs. This scenario underscores the critical importance of thorough considerations in designing, building, and operating safety-critical systems. Efforts must be devoted to anticipating potential issues, evaluating their likelihood and consequences, and developing strategies to avert, mitigate, or detect risks. One effective approach in this regard is the implementation of a formal risk analysis, ensuring a systematic examination of potential pitfalls and the implementation of proactive measures to enhance system safety and reliability.